Hello, everybody, and welcome. I'd like to introduce Dr. Josh Semeter, who is a Boston University College of Engineering professor of electrical and computer engineering, and as well the director of BU's Center for Space Physics. You may remember him presenting with Michael Hunnicull a couple of years ago, but he is here today to talk about a new project that he's working on, and I will pass it over to you, Josh.
Hey, I'm just going to plug in my computer, make sure that failure doesn't happen. Thanks for that nice introduction. It's good to see everybody. Let me try to share a screen with you all.
Seeing it really nicely.
Very good. Okay. All right, so yeah, good to see you all. I'm going to tell you some perspectives on UAP, tell you what that stands for and why. I'm going to assume people aren't overly familiar with this topical area, maybe just peripherally, but I've been looking into some of the data in considerable detail, and I've had some very lively debates with people out there in the citizen scientists who are trying to do their own type of analysis and introducing their own type of biases. And so I'm going to talk about some of that. And so yeah, I've worked with Michael Hunnicull, also Vince Ledvina, and Elizabeth and others in the Aurora community quite a bit. I'm fascinated by the Aurora, and I've often tried to find succinct quotes that sort of represent my perspective on research. And this one by James Joyce is actually, I think, the best I've found so far. In the particular is contained the universal. And so very often when you're trying to understand a phenomenon, it's the little detail that sort of breaks the whole magic and reveals the physics or the underlying cause of some kind of observation. Hopefully some of you can resonate with that and have an idea of what I mean. So back in the early 2000s, and then again in 2014, we started to see a release of some infrared videos recorded by Navy aviators, and that made a lot of hot press. It's really easy to monetize spooky things, and so a lot of those observations were immediately attributed to alien intelligence and so forth. And it became clear that there needed to be some body of people looking at this phenomenon, at these phenomena, from a purely scientific perspective, and with kind of a reputation of being unbiased towards their approach to things, and also fully transparent, in that NASA turned out to be a good organization for representing that perspective. And so NASA put together a UAP study panel, and it was a really interesting panel that they assembled. This is kind of the makeup, if you will. There were a couple astrophysicists, FAA representatives, mathematician, some people from the defense sector, Scott Kelly, our resident astronaut, and some space physicists, planetary physicists. There was an oceanographer, and some data scientists, and some NASA administration personnel. And so we had a charge. I didn't produce a slide for that, but our charge was really around not so much analyzing individual events. We have looked at all of the unclassified material that has been floating around in the public sector and has been aggregated by the DoD in their new all anomaly resolution office. And but we weren't given any exposure to any classified information. And we're not sure what that would show actually at this point. Okay, so we have, some people call it a rebranding, but it's really a broadening of the concept of UFO. This is the reasoning behind coming up with a term unidentified anomalous phenomena. With UFO, there's an automatic stigma after 100 years of suspicious objects and interpretations involving extraterrestrial intelligence. And with UAP, we endeavor to have no stigma, and hopefully we have none yet. What we want to do is treat all anomalous phenomena, whether it be in the air, in space, in the ocean, on land. So not just flying objects, but all manner of objects and phenomena that might be attributed to something anomalous. Okay. So my motivation to join the panel was actually quite simple, and I don't know if it's reflected in other people in the panel, but I really and truly wanted to see something that was extraordinary. But I don't want to invent magical explanations either. So I really wanted it to be real, and I was looking forward to seeing very direct evidence for extraordinary maneuverability, or basically, propulsion systems that don't exhibit any thermal signature, all these things that you start to hear about. And I wanted to find those and make my own judgment on things. So I'll leave that there for the moment. So my contribution, I have some, from working with the likes of you and others through the years, I have some idea of how to think about remotely sensed objects that look unfamiliar. I know something about optical sensors and the types of games they can play with your brain based on their insidious ability to produce image-like phenomena within the optical system itself that's unrelated necessarily to external objects. So I was hoping I could contribute some of that quantitative analysis to this panel. I've already mentioned why NASA, in that we purport to be a transparent organization. Our panel was not NASA affiliated. We were commissioned by NASA. And so we sort of represented NASA as employees, if you will, for the duration of our panel activities. And then, the scientific method is really what we hope to bring to bear on UAP. It's worth mentioning it, even though everybody kind of knows what we're talking about. But basically, we're going back to Rene Descartes in the 17th century. And the idea is that you can make up any conjecture, any hypothesis you want, but it has to be robust to data that's coming in. And as soon as even one solid piece of evidence refutes your hypothesis, you are compelled to change it. And so for instance, a lot of the stuff I'm going to show you has, as accompanying data, testimonies of pilots in terms of what they saw or what their friends saw and so forth. And I have endeavored to stay strictly and rigorously to the data and almost pretend that nothing else exists except what's measured by the sensors. And I think that's the best way to move forward with understanding these anomalous phenomena. As Carl Sagan put, extraordinary claims require extraordinary evidence, and we need to understand that if we're going to make these extraordinary claims, then there has to be direct, solid evidence. And with lack of that, then we have to retreat to a probably more likely explanation that does not require the extraordinary claim. So we're really good at, through the years, the sensors that look at the natural atmosphere have accelerated in amazing directions. This is actually somewhat an old video at this point, but I just want to raise the point that our community, Aurorasaurus and other communities that look into the night sky with very high resolution sensors are used to seeing things that are unexpected. I mean, the lightning bolt, this sort of immediately tells you that your general image of the formation of lightning based on, this is actually a movie that's still playing right now. So this is obviously the thing that you see when you see lightning. And you need to look at 10,000 frames per second to understand the formation mechanism of such a phenomenon. And, sprites, we've had recently some amazing new high definition images of sprites. These things flicker on and off in microseconds. And we can now look at them not just at 10,000 frames a second, but we can look at them at 100,000 frames a second.
And then they do some basic circuit stuff.
And so this is another example of where if you have observations of this type from multiple directions, say, then you can start to triangulate the pieces and parts that comprise that image. And these are the sorts of things that we have developed within our communities, and that we can bring to bear on UAP phenomena as well. Of course, this is a beautiful Steve movie that Michael and I worked on together at one point. This is from Alexei Chernenkov. And so we continue to find new and unusual phenomena in the atmosphere that's not readily explained by current existing theories. So we're good at all that kind of stuff. So it's really, our community has a lot to bring to the UAP issues. Okay, so the DoD has stood up an entire office related to UAP, run by Dr. Sean Kirkpatrick. And this office is called AARO, so this is the All Anomaly Resolution Office. And they've done a nice job of trying to summarize what's been observed so far in terms of these unidentified anomalous phenomena. And so here we have some basic reported characteristics. Not too surprisingly, from my perspective, most of the objects reported are round. And we don't really know the size, but where we have a conjecture about the size, they tend to be sub 5 meters. And there's some information about the color, velocity stationary to Mach 2. I'm actually not sure how reliable that is. In order to figure out the velocity of an object, you need to know information like its bearing and its range, and to good accuracy and things like that. The main thing I want to say about this is that these kinds of charts of typical characteristics are useful to sort of get the range of phenomena in different categories that we're talking about. The danger comes in conflating them as being all applicable to sort of a single phenomenon, right? So UAP is very likely a combination of space junk, drones. There's a lot of different targets up in our airspace right now, and we really have to treat each observed event individually. So the pilots have gotten better at reporting observations of strange phenomena. There is a major concern about just aircraft safety based on these things. So in addition to sort of trying to understand the physical nature of these objects, almost independent of whether or not anything extraordinary is going on in that domain, we absolutely have to understand these objects so that we're not ingesting them into our jet engines and compromising aircraft. And so one of the goals of that office and the UAP movement, if you will, in general, is to destigmatize reporting UAP. And we've come a long way in that regard. Again, there's a pie chart with object types that people have reported, and the majority are reported as round spheres, orbs, if you will. And then lastly, in terms of the AARO contributions here, the objects are not, of course, uniformly observed, sampled across the planet. There are hot spots in Southeast Asia and the US, where on the coast in particular, where we observe more of these objects. So we don't really know how the reporting looks in a kind of uniform, globally sampled fashion. Okay, what I thought this group might be interested in actually looking at some data. And I am very interested to know your feedback, your comments on this type of thing. I don't know how many of these events you've looked at yourself, maybe even just in the popular media. But we can look at these with some rigor and some quantitative detail. And that's an interesting thing to do, because who doesn't want to figure out, how something works? So one of the events had a nickname called Go Fast, and it looked like this. It was Navy aviators from the aircraft carrier USS Theodore Roosevelt in 2015. And this is an at-FLIR, a Raytheon targeting pod detector affixed to the FA-18 Hornet. And of course, it locks onto targets if it can find them, and produces data that looked like this. So the pilots were very excited to lock onto this feature. And what's interesting is that we don't have to speculate necessarily, or at least not 100%, on the flight characteristics of this object. And I thought that this was a potentially good example to illustrate the bias that can occur through the parallax effect. This gives the impression, this object, of some kind of a small, maybe spherical shaped object skimming along the ocean in the background at some kind of extraordinary velocity. But if we look at the information on the display, then we can actually come up with a hypothesis that has a more prosaic explanation. So the information on the display includes the elevation and azimuth of the camera, the target range in nautical miles, the aircraft altitude in feet, the time reference in seconds, and then an indicated airspeed in knots. So we have all these beautiful mixture of units that you have to contend with when you're doing analyses of this type. So one of the things you could imagine doing is take each of these parameters as being deterministic and accurate. And we can talk about whether that's the case somewhat later. In particular, the target range, it's not exactly clear how accurate that is. But we can certainly do some geometry on the parameters that we have. So what I've put out here is a vertical plane of altitude versus distance. The jet's at 25,000 feet, and the object is at, converting things to feet and miles. The object's at 3.8 miles range. The elevation angle's downward at 35 degrees. And so you can do some simple high school trigonometry and figure out that object is at 13,000 feet. And it's basically midway between the jet and the background ocean. Okay, so what you're looking at is an object that's actually not skimming along the ocean. To the extent that the ranging is reliable, that object is 4.2 miles from the background ocean. Okay, so what's the conclusion from this basic analysis? Well, it's that parallax will contribute to the apparent motion. All right, so one of the challenges, if you will, is that this targeting pod locks onto a target and gives you the impression that you're on a stationary platform looking at an object that's moving. And so you can do these little parallax experiments yourself by sort of putting your finger in front of you and sort of moving your head versus moving your finger. They have indistinguishable effects on the image received by your brain. Okay. So then the next level of analysis that you could do on this requires some modeling that has uncertainties in it. All right. So we have, as you saw, a movie with the target on lock. And we can start out, we could set time 0 anywhere we want. All right. And we can make a model of the jet's flight path. All right. So this jet is banking to the left at about 15 degrees. We can use some calculators to estimate the radius, basically the curvature of the flight trajectory. We can register the azimuth and elevation at the start and end times. We have a range that went from 7.32 kilometers to 5 kilometers during that period. Essentially, we have a nice overhead planar geometric picture that we can produce to try and estimate, in the absence of any other further modeling assumptions, how fast that object was moving. And what we find is that in the 22-second interval, it moved about 0.4 kilometers. It moved about 400 meters in 22 seconds. And this corresponds to about 40 miles per hour. All right, and so I'm not the only one who's sort of done this analysis. Others on the internet have, and have kind of corroborated this basic calculation. So the finding here is that under a zero wind assumption, the object is actually moving at about 40 miles per hour. And one can state that this is consistent with wind speeds expected at that object's altitude at 13,000 feet. And then furthermore, the bright color of this object against the background indicates that it's colder than the background ocean. And that suggests that there's no active propulsion system. So we're not seeing any evidence of jet exhaust or any such thing. Okay, so one might be tempted to conclude, well, that's the end of the story. This is perhaps a balloon, some other kind of aerial junk that's kind of drifting with the wind at 13,000 feet. But there are those that will raise the contention that you have not included the wind adjustment, and that's fine. The pilots were self-reporting very strong winds at the jet altitude during this event. And so, although the wind field is variable and not directly measured everywhere and a function of where the target is and where the jet is, we could run a model like this over a range of plausible wind parameters on this night. And we can look at how the results change. And interestingly, you know, under a headwind assumption, the object actually switches directions and moves in the opposite direction relative to the aircraft starting point frame of reference. And if we start to relax the wind and we let the wind shift directions, the radius of the flight path changes and we get different results indeed, not surprising. And the finding there is that considering plausible wind adjustments, the object's ground speed was in the range of 0 to 120 miles per hour. Other people may use different models and get somewhat different results, but my conclusion from this is, okay, we have to adhere to the scientific method. What is our hypothesis and how does the data support or refute it? The conclusion I would draw from this is that there's no extraordinary means of propulsion needed for this object. Okay, it's not as if it's requiring any kind of, you know, anti-gravity propulsion technology or any other such thing. If it is under propulsion, perhaps by rotors or something that doesn't produce a lot of heat, the propulsion that's required is not extraordinary. Okay, and this leaves then, we can partition what's left in terms of trying to decide what this object is into two hypotheses. One, the object had a non-zero airspeed maintained by a propulsion system that produced no discernible thermal signature. That is a hypothesis that many people want to be true and have been trying to justify that hypothesis. Another is that the object was drifting with the ambient wind, so that it had zero airspeed, and this is consistent with lack of any thermal signature. I can tell you, yes, I tend to favor item 2, but I am willing to concede that hypothesis 1 is still a possibility for this object. But the main point, and we included this this little analysis in our report, and the main point was to try and educate, if you will, you know, the general public that might be interested into the types of tricks the physics can play just based on the parallax effect with a distant background, a distant structured background, and an object that's more in the near field. Okay, you know, here's an example that shows it more clearly. When you have sufficient context, your brain stops making, it'll change its bias, right? So if I were to tell you that this star-shaped balloon is moving at an extraordinary velocity under no propulsion, you would shake your head and say, no, that's certainly not the case. This object is in fact stationary in the frame of reference of the wind. There can be little doubt about that because it is a balloon. And the apparent velocity is due to the aircraft filming it, moving by it. So this is just to highlight the parallax effect, okay? All right. Another object that we see. Loud. That has received a lot of attention. This this object called the gimbal.
It's not LNS though, is it? It's not. I do. Well, if there's like, it's roasted.
Okay. So this one has garnered a whole lot of attention because it looks like it's exhibiting crazy maneuverability. It has no air, control surfaces or airfoil surfaces. It's got no propulsion that we can see. And just to highlight a few of the pilot comments, there's a whole fleet of them. They're all moving against the wind. It's rotating. And, if let's take a closer look at what might be happening here. Some instrument factors. This is an extremely narrow field of view. I believe it's about 7, it's either 7 or 3.5 degrees. The object has an unknown range, so there was no ranging on to know where this object was. And the other point that kind of, as I've said before, breaks the magic of the event is that the object rotation, that object is actually rotating with the sensor. It tracks the rotation of the sensor. You can't see it in this display because what's happening is that the software is derotating the background so that the pilot sees a sensible representation of the background with respect to what they see out the window. And, so I thought I'd show you the thing that, very early on, the very first time I saw this video, there was something in it that really bothered me. And I'm going to go through a couple frames here. And what I want you to look for is the jostling of the camera just prior to the rotation. And it just happened. Those are some frames. We can. Yeah. So frame 3, 4, 5, and you'll see that the object actually moves a little bump up and down right before it begins its rotation. And you find that each step that the object rotates, there is a little bump in the camera just prior to the rotation. So what that means is that either the object communicated to the camera that it was about to rotate, or there's some physical connection between the rotation of the object, a causative connection between the rotation of the object and some adjustment that the camera is making. And I don't really want to spend our entire time here going through the excruciating details, but the answer that's irrefutable appears to be that the structure we're looking at is in fact a signature of the glare in the camera and not a direct signature of the object as it looks in space. And the basic explanation, courtesy of Mick West, I borrowed one of his videos, can be seen here. Whatever the glare function is in a camera, it's going to follow the camera around. All right. And so the background can stay stationary and the glare function can rotate, giving you the sensation that there's something in object space that's rotating. All right. All right. And what the reason this works is because the if any of you, as I know many of you probably have, you've played around with different types of astronomical mounts. LAS mount. This is a gimbal mount where you have one rotating dimension connected to another. And there's sort of a singularity in gimbal mounts as you cross through its forward-looking position. In other words, the rotation of the two axes, there's multiple solutions for it. And so you have to sometimes do a rapid rotation in one direction and a small adjustment in the other. And so what you're doing is rotating the sensor in a kind of extreme fashion. So you're rotating any glare function that might be produced. And then you are derotating it again in your image processing to display to the pilot. All right. So I'll show you one more that you may or may not have seen. This one's kind of fun. This is another observation. This is by infrared. I think it was a night owl camera, maybe, of green triangles flying around overhead. All right, and this is as we zoom in on it, we get a really nice crisp image of a pyramid-shaped or a triangle-shaped object. So this one was actually quite simple to debunk. Well, I don't know if debunk's the right word, but just explain correctly. You know, if you look at it, whoops. Yeah, if you there we go. Yeah, if you look at the video here, you see different triangles within the scene, and these are what this is essentially you've kicked this thing out of focus a little bit, and the aperture of the camera has a triangular shape to it, and so this is called the bokeh effect. And it took actually some years to come to the right explanation for this UAP video, but it has something to do with this sort of thing. All right, so if you crank down an aperture and the aperture becomes close to the focal plane because you're out of focus, then you're going to be imaging the aperture as a point spread function, as an effective point spread function. So these are either, I believe these were turned, the large blinking one was determined to be an aircraft in the vicinity. Okay. So there are other events. The thing that's, you know, what the take home from this that's really extraordinary to me is just the many and varied ways that an optical system can trick you. All right. And going back to the original kind of theme I started with, I mean, I think we really do need to be very careful about adhering to the scientific method. And I do think it's the right approach to go in with kind of a skeptic's eye towards extraordinary interpretations. You need to define your hypothesis space and then see what the data tell you. So what has happened with our recommendations in our report? Okay, so the first one is just sort of a blanket picture. There were other more detailed recommendations that I can leave to you to read about concerning the application of AI and so forth. But one item that's been acted on is NASA has created a dedicated NASA point of contact for UAP. I think that's good. I don't think it needs to be a very large office, but I think it needs at least one person that can coordinate with the DoD sector, with citizen scientists, commercial sector, around these objects. One of our recommendations, maybe it sounds a little kind of unclear, if you will, but establish a baseline data set for sensors being used. So we would avoid a lot of effort if we, for instance, take the Raytheon sensor, right? If we actually had kind of a taxonomy of what's observed, what different objects appear like to that sensor, we could probably, you know, even capturing and categorizing the glare function. And that's what we need. We need to start to build up this baseline of data that sort of leaves as the remaining phenomena, the unexplained stuff. Okay, and then citizen scientists play a potentially huge role in UAP, right? And there are companies trying to monetize this, and that's fine as long as they are, you know, the input to the sites is monitored in some fashion. But if you think about the ideal contribution of crowdsourcing in citizen science, it's very much akin to what Aurorasaurus is doing. I mean, you have a responsive network of passionate observers who are willing to deploy themselves to look at something in the sky on a moment's notice. I mean, sort of the news that there's some strange thing overhead, please go out and take some data, is very likely to be responded to. And the other thing that's exciting is that it's self-validating. I mean, it's very difficult to create fakes when you have 30 or 40 different people looking at the same thing from different directions. And that's kind of an exciting opportunistic consequence of crowdsourcing. And the other thing related to that is that you're going to get multiple viewing angles. So as long as, if we can get to a culture where the metadata is reliable, then you're going to have a situation where you can routinely do tomographic, stereographic analysis of these objects, which tells you not only the altitude, but as I was trying to show, it also will give you estimates of velocities and excuse me, and trajectories. Okay, I don't actually know how long I've been yammering on, but that's all I had. I'd love to hear some comments or discussions.
Thank you so much. That was absolutely fascinating. I know we have about 12 minutes left, and I know Jeremy had some questions for you. Jeremy, do you want to ask some of your questions?
Thank you. Thank you for the presentation. I really appreciated that perspective. I was trying to think of a question that, like you said, applies to any community that's trying to analyze through categorization of sightings a phenomena and learn something from it. And I guess that's the overlap between this topic and, say, the aurora, where some sightings are understood, others are not. And I was curious about when you only partially understand a phenomena and you want to do analysis of it through recording sightings or events, how do you come up with a categorization system that doesn't sort of overfit or underfit the data so that it obscures particular phenomena or overemphasizes them? Sort of one thing I can think of is if you're making a histogram, how do you choose how many bins to have? That's a very, I guess, a simple way of saying it. But when it's something that's being reported by people and it's something that's undergoing analysis, how do you choose how to make categories for your data set? Thanks.
Yeah, I'm actually really excited about that question because it reminds me, I come from an engineering background and sort of a signal processing radio science type background. And a data point has no value without an error bar, right? And 100% error bar is still fine, right? But as soon as you move to a stochastic representation of the world, right? And we have textbooks and a full theory for how to do that, how to do detection problems, estimation problems, system identification problems that are where the data is not just, the data is considered the mean of a stochastic distribution. And if you want to move forward, you need to know how reliable, right? If you told me, if I tell you, well, the phenomenon I'm looking at is 100 kilometers away, the 1 sigma variation is 100 kilometers. So that means to the confidence interval, the 70%, if you will, confidence interval of the range is between 50 and 150. Now, I need to know that because that may invite into that range completely different explanations for a phenomenon. And your comment that you want to, I really like what you said about partial understanding too, because that a partial understanding almost implies that, well, I'm moving towards understanding, and I'm partway there, and now I want to go the rest of the way. Whereas other times, understanding, you find an impasse and you need to move from classical physics to quantum mechanics. There is partial understanding doesn't apply. You need to break the whole thing down and build it up again with a different model. So either one of those things can happen. It could be that you just want to tighten the error bars to figure out is this moving at a hypersonic velocity or just a supersonic velocity, both of which are explainable with standard propulsion, okay? But another case is like, oh, holy crap, this thing is moving at Mach 40 through air with no discernible propulsion signature, right? You need to, if we found something that looked like that, we'd have to start looking at completely different hypotheses, like maybe it's a hologram produced by, a set of satellites or some such thing. I don't know if that addressed any of the stuff you mentioned about it. If there was a topic you mentioned that you wanted more comment on, let me know.
Thank you very much.
Yeah, you're welcome.
Um, Joshua, I just wanted to ask in that first example, and by the way, I really enjoyed the presentation, especially the cell phone being used to show the rotation, because that's something you could demonstrate to anybody, and it's a total aha moment. It makes sense. But the one thing I asked or wanted to ask was, or maybe I missed it, what is the estimated diameter of the first object that you discussed? You had all of the data about it, but was there a size?
Yeah, some people I've stayed away from that as being resolvable in my analysis. I don't remember honestly what people have reported, but they've blown it up. They've taken, of course, the assumed range, and it's sort of 3 pixels wide and that kind of thing. And I think they found the object to be in the range of single meters, but it's unclear again what does an object, what is the system response function in the infrared, right, to an object that's at 4 miles away. Like at some point we need to sit down with the people who designed that pod, because it may not be an accurate or useful measure to take dimensions from an infrared video like that. That would be my response. But I think the short answer is I think it's in the range meters, and I can go check on that.
Thank you.
I am so fascinated by how UAPs, or UAP, I guess is plural, require, similar to Aurora, such a range of interdisciplinary expertise to approach. Because I've noticed as I've gotten to know this community, there's so much cool stuff that happens when you get physicists and photographers and people who live under the Aurora and other expertise in the same room to talk. And I just love that your panel has so many different perspectives. And you talked a little bit about wanting more citizen science perspectives, but what other skill sets do you think would be useful to bring to bear on this topic?
Well, if I were to immediately jump to the provocative, I would say psychologists.
Yeah, Mandela effect.
Because the people whose opinions go towards the extraordinary, if I could divide them in 2 camps, I would do it this way. There's one that just needs there to be an extraordinary explanation that involves extraterrestrial intelligence, and they don't have any training in sort of basic analysis, how sensors work, that sort of thing. They're not necessarily technically literate. All right, but then you find the other people who I can't remember, is the term confirmation bias. They've spent sort of 5 years working on their model of the thing, and it never occurred to them to think about the glare function and how that rotates with the sensor, and the fact that it's on a gimbal mount, this little nuance, if you will, that kind of upends the whole event in terms of it being extraordinary. They don't want to let that go. I mean, they've done trajectory analysis through wind fields and all these sorts of things to show that, hey, no way could this possibly be a standard object of any type. But in reality, the explanation becomes quite simple when you consider that piece of physics. So I guess when I say psychologists, I'm not trying to be glib. It's just that I'm really interested in how people develop their biases, and I certainly have my own. And how the behaviorists like Kahneman and Tversky, they studied all this stuff, how you get locked into a certain interpretation and it's really difficult to let it go sometimes. And I'm hoping if NASA continues down this road that they even have it on the wall, you know, like just scientific method, just, you know, this has to be purely data driven. We cannot rely on accounts of people. We cannot treat that as data. Okay. I mean, so for instance, you're probably all familiar with this guy, David Grush, who came forward with reports of having talked to somebody, I guess, who's witnessed alien life forms that are, you know, basically dead UFO pilots and things like that. And there is, he's not able to produce any evidence, and even the people that he's reporting secondhand from can't produce any evidence. And we're always left at that impasse. And I don't know, you know, I don't know what the motivation is, or how to think about, you know, that sort of speaks to me about all of the personal testimonies that are sort of being appealed to as data, is that I think the best high ground for us as a scientific community to take is to just demand the data, its error bars, and what conclusions can be drawn from those sources alone, irrespective of whether there's a huge amount of context from personal accounts and eyewitnesses.
Thank you. Yeah, it's really interesting. And I think the idea is interesting to me that a balloon flying over the ocean isn't wondrous enough, or that a bird moving at a very rapid speed isn't thrilling enough. You know, that the idea of like what constitutes extraordinary, and I put in the chat, it reminds me of a quote from the author Terry Pratchett. Humans make life so interesting. Do you know, in a world full of wonders, they have managed to invent boredom.
I like that very much.
Yeah. So I think we have time. We have about 5 minutes, and unfortunately, I do need to use the Zoom account for another meeting on the hour. But we think we have time for one more comment or conclusion. Or Bob, I saw you raised your hand there for a second.
Yeah. Just like class, right?
Yeah,
I just wanted to ask Joshua, if you were to give one message to, say, the public about what they should do should they see a UAP, you know, scientifically, but simply, what would you advise them to do in terms of capturing data?
You know, it's interesting because the Aurorasaurus platform could be a place that sort of is it one place where accounts of things other than the Aurora are also reported and mapped. Right now, I don't think, you know, we don't have a hotline set up for UAP sightings. And there is, you know, at least one company called Enigma Labs that's trying to create that platform. And it'll be interesting to see, you know, whether it gets polluted and spammed and all that kind of stuff, trolled. I don't know. But yeah, Bob, I don't know, like, what my advice would be. You know, if you see something extraordinary, you should say something. But we don't really have a central repository at this point.
Even outside of a central repository, but let's just say the person wants to record the data, you know, first maybe you'd want, right, just sort of a scientific way of doing it that the public might understand. Like if you're giving a talk, for instance, to a very general audience.
Yeah. Well, one thing I would say is that, you know, it really pays to have accurate and reliable metadata, and you should make sure that that you, whether it be your camera or your phone, you know, if you really need to know position and bearing to an object, and you're mostly there at that point. What I would do, yeah, so I'm sorry about thinking aloud here, but you know, if I'm out in Westboro, Mass, and I see something strange overhead, I would immediately call somebody who's a few miles away from me and ask them to run outside and take some video of it as well. Because as soon as you have those 2 points, it's not quite enough, as you can imagine. You kind of want 3, but if you have 3 observations of the object, I can tell you its altitude and its velocity in 3-dimensional space. And that immediately narrows down the plausible objects that we could be looking at.
That's great. Thank you. I mean, it seems obvious, but that's really great to hear. It's a simple thing that anybody can do.
Yeah.
Well, thank you so much, Josh. This was fascinating, and I know I've got a lot to think about, and I know everybody here is going to get really excited when they see new observations and things. I know Rocky said he would post some interesting things he saw to social media, and I will make sure that you have the chat afterwards that you can read through people's comments. But I just want to thank you all again for being here today. Enjoy the annular eclipse tomorrow if you are in the path of it. As always, please stay safe. Do not look at the sun without glasses, all of that good stuff. Obligatory safety message. But thank you again, Josh. This is fantastic. And we will see you all next month. All right.
Thanks. It was terrific talking with you all.